Hi and welcome to the second part of my Carbon-13 MRI transmitter coil series. This time we're going to talk about nuclear magnetic resonance, which is inherently a quantum phenomenon, but we can apply a lot of different mechanical analogies to understand it better. So this is the second video in the series. As you can see here, I have a few different videos planned. We already went through the introduction, and we're gonna learn some basic theory behind MRI in this video. So throughout it all, I'm going to assume that you have a basic high school level physics understanding. I'm gonna assume that you have differential calculus knowledge or higher. I'm also gonna assume that you have basic electromagnetism skills and very basic acquaintance with quantum mechanics. But do know that I am not an expert, and I'm mainly making this video for my own understanding and to convey my knowledge outwards as a kind of way to prove to myself and to others that I've actually gotten something out of this project. This is more of a documentation video and is therefore not recommended as educational material. You'll also notice that throughout this video there are going to be different colored boxes around the screen. So far you've only seen orange, which is general knowledge. It doesn't require anything specific. But you'll also be meeting purple boxes whenever I explain a concept or phenomenon through quantum mechanics. And green boxes for classical mechanical kind of intuition. I'm gonna be going through both several times to see the parallels between them, and also like the green boxes end up being more of a simplification of the quantum phenomena. So the MRI process is actually fairly complicated, but overall it can be divided into these boxes that you see here. So very briefly explained, the patient is placed in a static magnetic field called B0, we'll get to that. And on top of this field, we also add gradient fields, so fields that vary across space. That way we can associate different areas of the body with different voxels or 3D pixels. We then excite these magnetic dipole moments inside the patient, which are a bit like small bar magnets. And when we release this excitation, they start to decay again, they start to relax. And through this relaxation process, they go through something called free induction decay, which is essentially a process where they induce a signal in a receiver coil. And that receiver coil signal you can reconstruct into the image that you see in MRI. I'm not going to at all talk about that reconstruction though. In this video I'm going to be focusing on the first 5 boxes of the process. But before we start, I'm going to be mentioning a lot of words related to the orientation in an MRI. When a patient is in an MRI, we usually classify the direction from their head to their toe along the MRI as the z-axis, and then the x and y axis will take up the transversal plane, which is always perpendicular to this axis. There's also the coronal and sagittal plane, but we're not going to mention those in detail in this video. Usually the x-axis ends up being from shoulder to shoulder, whereas the y-axis ends up being up and down physically in the room. So all of nuclear magnetic resonance builds on a concept called spin, which is an inherent quantum mechanical property. Just like charge, you can kind of understand it as an intrinsic angular momentum, and it usually has a fixed value for each type of particle. And with this spin, imagine it as like a spinning motion of the particle, you can kind of imagine that a charge in motion would create a magnetic field. So with a spin, there's an associated magnetic moment, which we will touch on later. A special type of spin is called spin half, which is an intrinsic angular momentum of the reduced Planck constant. That's the Planck constant divided by 2 pi over 2. So it has 2 projections, 2 allowed modes, you can say. Spin up and spin down, which is plus Planck's reduced constant over 2 and minus Planck's reduced constant over 2. MRI usually only uses spin halves, because anything above spin half will have a non-spherical charge distribution. We call those a quadrupular nuclei. The thing is, we need a uniform spherical charge distribution if we want like a stable signal in the MRI. Quadrupular nuclei just do not meet those requirements. Excitation is going to be very hard with a non-spherical charge distribution. And as I mentioned before, you can kind of imagine spin as a rotational motion of the particle that creates a magnetic moment. And the spin can be either up and down, represented by this arrow, perpendicular to the rotational motion, which we call the magnetic moment. So spin up and spin down are actually just different rotational directions. Now, in the nucleus, there's going to be many different particles with many different spins. And these spins, they interact with each other, actually. They actually cancel out. So a spin up and spin down will cancel out and become nothing. In most cases, there are, of course, outliers. But in general, a nucleus with an even amount of nucleotides will end up cancelling out, so there's no net spin. Whereas an uneven amount of nucleotides will result in a net spin of above zero, a non-zero net spin. Why don't they just all have spin up or spin down? Well, that's actually because of the Pauli exclusion principle. The Pauli exclusion principle states that no two identical fermions can be in the same spot in space. A fermion is a particle like an electron or a proton or a neutron. And so if they can't be in the same spot in space, they have to adapt. And how can they change their properties so that they're not identical anymore? Well, they change their spin direction. That results in a spin cancellation, as you can see, which is very important. This explains why some particles like Carbon-12 do not have a net spin and can't be used in MRI, but Carbon-13 can be used in MRI. Now, I mentioned briefly something called a magnetic dipole moment. Electric charges create electric fields, but for magnetic fields, we don't have a charge that creates a magnetic field. So, instead, we have magnetic dipole moments to represent these magnetic fields. They determine the interaction with the magnetic field, but they're a little bit more complicated than charge because they're a vector, which means they both have a modulus and a direction. There's both an intrinsic and an induced magnetic moment. We're only going to be touching on the intrinsic magnetic dipole moments in this video, as those are the ones caused by spins and other quantum phenomena in nuclei. We represent this with the Greek letter mu, and it's proportional to the spin angular momentum of the system. You can see I've kind of showed it in two ways, both with the classical angular momentum and with the s, which is the spin angular momentum. There is no actual angular momentum in this, but it's just a nice way to represent it. And we're going to use it mechanically, classically, as angular momentum later in the video. And the proportionality factor is called the gyromagnetic ratio, and that actually depends on the different isotope. And so Carbon-13 will have a gyromagnetic ratio different from hydrogen-1, for example. A standard MRI scanner utilizes 3 different types of coils, roughly. The first one is the main coil, that one you'll see on the bottom, it's the orange one. It just produces a steady magnetic field, a very strong one, usually in the orders of 1.5 or 3 Tesla, although research MRIs have actually gotten up to 10 Tesla, if I remember correctly. And we call this magnetic field B0. It's very important. The purpose of this field is to align all magnetic dipole moments in the patient in the same direction, basically. And as you'll hear later, they will start precessing around this magnetic field, kind of spinning around, which is actually what's used in MRI to generate the signal. Then above that, you'll see a blue coil. That one's the gradient coil. I've only shown it for the z-axis here, but there are separate gradient coils for the x and y axis as well. This configuration is called the Helmholtz coil configuration, and it produces a linear gradient of magnetic field from one coil to the other, which is very useful if you want to select specific slices of the patient along the z-axis. And finally, the one I'm going to be making is the green coil at the top, the transmitter coil. The one I've shown there is of the type birdcage coil, named after its appearance, which resembles a birdcage. The purpose of the birdcage coil is to function as a quadrature coil, which generates a rotating magnetic field. And if you rotate this magnetic field at the same frequency as the Larmor frequency, which we'll touch on later, you can excite these magnetization vectors, which is the sum of the magnetic dipole moments. If you spin at this magnetic field at the same frequency as those, you create what's known as resonance. Essentially, you excite these magnetic dipole moments so that they end up being close to perpendicular to the coronal plane. And, as we talked about before, if you let go of this excitation again, they will start to relax and induce the signal in the coil, in the receiver coil. So I haven't drawn the receiver coil on here, mainly because I'm only going to be talking about the transmission. I'll be touching very lightly on the receiving part of MRI at the end of the video, but it's not the main focus, so I'm gonna be touching very lightly. So here's an example of what it might look like. This looks to be some gradient coils. I got this from ctmrihub.com. Yeah, so I mentioned something called the net magnetization vector before. And you can think of the net magnetization vector as a sum of all the magnetic dipole moment vectors in the patient. We'll touch visuals later, but for now let's just discuss how a net magnetization vector even arises. Shouldn't all this magnetic dipole moments just cancel each other out if they're pointing in different directions? They would in a patient who's not in a static magnetic field, but as you can see here on this graph, the energy difference of the spin up and spin down properties actually increases with the magnetic field that you apply on the patient. And this is known as the Zeeman effect, and it's really important because there's going to be two different main states of the magnetic dipole moments inside this magnetic field, and it's parallel and anti-parallel to the magnetic field. However, it's very important to still remember that it is quantum mechanics, so they can be in a superposition between them as well. We'll represent this with a hairy ball in the next slide, where each hair is a different direction it can have. But for now, just imagine it as parallel or anti-parallel, with an overweight towards parallel with the magnetic field. So, no magnetic field, they're pointed in random directions, and the stronger the magnetic field, the more they start aligning themselves parallel or anti-parallel with said field. But they can still be in other directions due to superpositioning. And we can represent this with like a hairy ball, with a weight, an overweight in one side. And this hairy ball experiences a torque, which we'll get into later. But for now, just know the visuals of the hairy ball. We don't need all these other vectors. They just kind of cancel each other out. So for now, let's just only take the overweight arrow, which we can represent like this. This is the net magnetization vector, and we represent it with a capital M. The energy of a magnetic dipole moment in an external field B is the negative dot product of the magnetic dipole moment and this external field. This is the classical way of understanding it, but when we're talking quantum mechanics, we don't use energy, we use a hamiltonian instead, represented by capital H. And it's almost the exact same formula actually. We just replace the magnetic dipole moment with our net magnetization vector, as that's way more important. We don't need to consider every single little magnetic dipole moment. We can just take the overall effect of it. That's what we care about in MRI. And with this, I introduced you Ehrenfest theorem, which looks really complicated, but it's not that bad, trust me. The time derivative of a quantum operator, A, in this case, you can think of a quantum operator as a mathematical object to represent like an observable event in real life. So the change of this quantum operator is equal to the change due to the system's Hamiltonian plus the explicit time dependence of this quantum operator. Now, here's some pretty complicated proofs. You don't have to understand it all. I don't. Which is again why this isn't an educational video. It's for my own understanding. We can ignore this last part and just have the time derivative of a quantum operator A be due to the change due to the system's Hamiltonian. Let's replace the quantum operator A with the net magnetization vector Mi, where I can be the x-axis, the y-axis, or a z-axis. And now we should have something like this. And remember that the Hamiltonian is equal to the negative dot product of the net magnetization vector and the external magnetic field. So we replace the Hamiltonian with that in here for the different axes. And then there's a rule in these kinds of operations where you can drag out a constant and separate the different parts of the equation. So we end up with something like this. And through this, there is a relation in angular momentum that looks like this. So we end up with I, which is the square root of -1, times the gyromagnetic ratio, times the reduced Planck's constant, times the net magnetization vector in each axis. And that should be equal to these three relations. There are tons of other combinations, but those will cancel out. For example, two of the same ones would be equal to 0, and if we swap the order of them, it's just the same thing, but flip, so we don't need that. These three are the only ones that will not equal to 0, and those we can actually use. And if we differentiate it, we end up with something like this, which we can summarize through the overall pattern of the three different equations into a formula that looks like this. Now this very closely resembles something called the Bloch equations, which we will touch on a little bit later. So keep this equation in mind, and you can see that there is a clear coherence between the classical way of understanding it, the classical proof of the Bloch equations, and the quantum mechanical way through Ehrenfest's theorem. Now I'm going to go through it classically as well. But to do that, we first need to understand torque on a magnetic dipole moment. And I'm going to do it in a really unofficial way through the Lorentz force. Do note that this is not the correct way to prove it, but it is a good way to understand it intuitively. So this is the Lorentz force. It's found empirically, as you know, and we can actually rewrite it as this, in this made-up mathematical way. And as we know, the torque is the cross product between force and the arm. So we cross an arm on, which is the same r as I just wrote before. And this is just equal to the area, arm times arm. That's the area. So we actually end up with the product of the current and the area vector crossed the external magnetic field. And per definition, the current times the area vector is actually the magnetic dipole moment. You can kind of think of the currents as these internal quantum currents that I briefly mentioned earlier in the video. So the torque on a magnetic dipole moment is the magnetic dipole moment cross the external magnetic field. The torque can also be written as the derivative of the angular momentum. And as we briefly mentioned earlier, the angular momentum is inversely proportional to the gyromagnetic ratio if we understand spin as an angular momentum. Remember, this is a very unorthodox way of proving it. And lastly, if we just replace the sum of every magnetic dipole moment with the net magnetization vector and multiply the gyromagnetic ratio on both sides, we end up with this equation, which looks a lot like what we just proved with Ehrenfest's theorem. And there's a reason. This is called the Bloch equation, and explains the change of the net magnetization vector, which is also the motion of it. Now what you can intuitively understand from this is that the change of the net magnetization vector will be perpendicular to both the external magnetic field and the net magnetization vector itself, which results in a kind of precession motion rotating around the axis, which I'll show you intuitively later. This is incomplete. It will be completed later in the presentation. This is just the first part of the Bloch equation. Now, at what frequency will this spin or precess around the axis? The answer is something called the Larmor frequency. There's two ways of proving this again. I'm going to do it quantum first, then classical. So the quantum way of proving it, a little bit unofficially, is through the Hamiltonian of the system, which, as I mentioned, is the negative dot product of the net magnetization vector and the external magnetic field. But we only need to look at the z-axis, which is the net magnetization vector along the z-axis, obviously, and b naught. So we don't have to do it through vectors, which means we can just multiply them together as scalars. Now the net magnetization vector could be written as the gyromagnetic ratio times the spin angular momentum. So let's do that. And as we know, the spin is only spin half, so we can assume either negative Planck's reduced constant over 2 or positive Planck's reduced constant over 2. Now there's going to be a lot more in the positive Planck's reduced constant over 2, because it has a lower energy level. So we're just going to completely ignore the negative one actually. So we end up with this. And now what we can do is actually divide by Planck's reduced constant, which ends up giving us the unit hertz. And what we actually end up having here is the angular momentum of this precession. And if we divide this by 2 pi again, we end up with the Larmor frequency, which looks like this. Now the pi has been absorbed into the gyromagnetic ratio. There are quite a different few versions of the gyromagnetic ratio. So for simplicity, this is the official formula for calculating the Larmor frequency. You'll also see the angular momentum, so omega 0, but that's a different gyromagnetic ratio. You should take that into consideration when calculating. Now that's also a classical way of calculating it, and you just take the Bloch equations in scalar form and then multiply the Planck's reduced constant to both sides. As you can see, we're only concerned about the right side of the equation. As you can see, we actually end up having the net magnetization vector times the gyromagnetic ratio times B naught times Planck's reduced constant. And this is actually the energy difference that we talked about in the Zeeman levels. So we can write it as delta E. And we know delta E is also equal to Planck's constant times the frequency of this wave. And now what we can do is actually isolate for the frequency. And we end up with this, which again we can absorb into the gyromagnetic ratio to get the same formula as before. So that's the classical way of proving it. Now I actually went back in the slide just to show you the processing motion of this with the torque. The pretend torque on the magnetic, the net magnetization vector. So it actually ends up processing, making this kind of conical shape around the z-axis or the magnetic field, as you can see here. And that's basically what we are trying to excite in MRI. And the way we excite this kind of precession is through something called quadrature coils, which in its simplest form is two perpendicular coils with a 90-degree phase shift. So you sequentially turn on one of them and then the other, and that way you can actually catch the net magnetization vector at the right moments and make it spin, if you do it in the right frequency, that is. And this phenomena is known as resonance. So there's a resonance between the quadrature coils and the net magnetization vector. Now, you can make this way more efficient by connecting a bunch of different coils with capacitors, as you can see here, which forms the basis of the birdcage coil that I'm going to be building, which is the standard within MRI. And as you can see, when you excite these net magnetization vectors, you create resonance. It's like pushing a swing. If you push at the right frequency, corresponding to the swinging speed, you actually end up going higher and higher. And in the same way, you can actually end up making the net magnetization swing higher and higher, or flip. It has a greater flip angle, which is the angle between the net magnetization vector and the z-axis. And that's the entire purpose of the transmitter coil, actually, just to excite that. If you do it in the right time frame, you actually end up getting close to a 90-degree flip angle. And when you release this again, you create the induction in the receiver coil, as we talked about earlier. Now, all these phenomena and the resonance and the transmitter coil will only work effectively in something called the near field, which is the area from the coil, much smaller than the wavelength, which in this case is 9.3 meters for Carbon-13 in a 3 Tesla MRI. So you gotta keep that in mind. The closer you get to the patient with the coil, the better signal you actually end up getting, which is one of the big reasons an MRI is always so claustrophobic and small. Now, why do these net magnetization vectors even relax in the first place again? Why don't they just stay up there? That's because they go through relaxation. And the relaxation is actually caused by two different processes, which are not correlated, but they happen at the same time. The first one is thermalization, also called T1. So due to the chemical environment inside the sample and due to thermal fluctuations, this net magnetization vector will start to lose some of its energy. It will kind of stand to fan out, and as you can see, and as it does, these transversal magnetization vectors start to have very little influence, so they cancel out and end up creating a longitudinal magnetization vector along the z-axis instead, which you can see by the thick purple arrow. And this is the T1 thermalization process. Meanwhile, there's something called decoherence, which we call T2, which happens because you can kind of imagine the spins as being basketballs. If you have a bunch of basketballs spinning on your fingers, when they bump into each other, they kind of lose a lot of energy, right? So some of these net magnetization vectors will end up going faster than other net magnetization vectors. And because of this, they'll end up being out of phase and cancel each other. And when they cancel each other, the net magnetization vector obviously becomes a lot weaker. The net magnetization vector relaxes both from T1 and T2. Now T1 is usually pretty stable and is used to generate specific signals, and so is T2, although there is something that also causes this dephasing, and that's local inhomogeneities. You can kind of imagine that the field isn't perfect, and the patient itself will kind of start bending these magnetic fields around them, and also the field is a lot stronger in the middle of the coil than towards the edges, and therefore you end up with these kind of different spots where different sub-magnetization vectors end up going at different speeds, and therefore giving out phase, and therefore they start cancelling each other out, just like before. And that actually ends up decaying the signal a lot faster than if you had just only had T2. There are several ways to combat T2 star, but I won't be discussing those in this video. I probably will in a future video. Now, this relaxation process can be represented by a vector added to the Bloch equations, finishing the Bloch equations. As you can see, the transversal decay is caused by T2, and the longitudinal gain is caused by T1. Now, as we discussed very briefly, when this relaxation process happens, it starts to fan out and kind of spin around in a conical shape, eventually returning to its original state. And due to Faraday's law, this will induce a current in the receiver coil, which is the signal you end up picking up. And this signal is what you eventually reconstruct into the image that you use in an MRI. Now, I'm just going to clear up one misconception that might have confused some people during this video, and that was me mentioning multiple net magnetization vectors. While there is only one net magnetization vector, there can be different sub-net magnetization vectors if different groups of magnetic moments start experiencing different conditions. Because of this, you can end up having different net magnetization vectors kind of cancelling each other out. Just wanted to clear that up in case it wasn't clear in the video. But that should conclude the tour through nuclear magnetic resonance. Again, this video should not be used as educational content, but rather it's documentation of my process through my project. And of course, it's inspiration for the curious individuals. In the next video, I'll be discussing the electrical engineering behind MRI. So what really goes on to kind of utilize this nuclear magnetic resonance. So I'm looking forward to making that video, and I hope whoever is watching this is looking forward to seeing it as well.